So we have our formula that lets us calculate work for a force that remains constant. But let's consider what happens if our force does not remain constant. For example, let's say we have a mass attached to a spring. This position here is the equilibrium position. And I pull the spring out to here, and then I let go. Well, the spring is going to exert a force. The force is going to pull back, and the mass later will be here. It eventually will keep going to the left, but I just want to compare from here to here. And let's say I want to know how much work does the spring do as it's pulling the mass to the left. How much work does it do? Well, the problem is I cannot use this equation because this equation depends on what the force is, and as my mass moves to different positions, the force that the spring is exerting will change, right? Because the force the spring is exerting depends on the x position of that mass. When the x position is over here, the force the spring is exerting is very big. The next moment, the mass will be here, and the force that it's exerting is smaller because that x displacement from its equilibrium is smaller. And as it goes closer and closer and closer back to the equilibrium, the force that's being exerted is smaller and smaller and smaller. So I cannot use this expression. What I would need to do is look as the mass moves from one position to a position just an infinitesimally small distance away. So such a small distance away that I can assume the force is constant over that tiny little distance, and measure how much work is done over that tiny little distance. Then go to the next tiny little distance and measure how much work is done. Then go to the next tiny little distance, and so on, and then add up all the work that I calculated. That process is also called taking an integral. So if we have a variable force, variable means the force is changing. If the force is changing, then in order to calculate the work, I need to take the integral of the force with respect to position. So the S here is just the generic way of saying position. If it bothers you that this is an S and you have no idea what's going on, just write this equation in terms of X. So this would be X initial and X final. And this would be F dx. Okay, so that would be your integral. Or you can also say this could be Y initial and Y final, and this should be F dy. That's what we're going to do when our force is variable, which is the case when we have a spring. Whenever you are taking the integral of something, you should be aware that if you plot this variable versus this variable, the integral represents the area under that graph. So if we had a force versus position graph, the work done by that force would be simply the area underneath that graph. Okay, so let's say we were doing this for a spring. I would need to know what's my initial position, so I could call this my x initial, and this would be my x final, which is 0 in this case. So whatever x initial is, I would plug in here. Whatever x final is, or in this case x final would be 0, I'd plug that in here. I would plug in the formula for my force into here. This would be a dx, and then I could solve how much work is done. Alternately, if I had a graph of force as a function of position, the graph of this equation, where this is on the vertical axis and this is on the horizontal axis, is just a straight line where the slope of this line is equal to negative k. And now if I want to know how much work is being done, I would just take the area. Okay, so going from some position over here to some position over here, I would take the area of this. Okay, mathematically you end up doing the same thing, taking the area of this graph that you do when you take the integral. So let's look at an example. You stretch out a spring with a spring constant 15 newtons per meter. You stretch that spring by 60 centimeters. And I want to know how much work does the spring do to return itself to its natural length. So I'm going to set it up where my x equals 0 is at the equilibrium position. And in that case, my x initial will be 60 centimeters and my x final will be 0. I need to know these values because these are going to be the limits on my integral. So this is my general expression for how to calculate the work of a variable force. And the force that I'm dealing with, this is the spring force. It's equal to negative k times x. And in this problem, k is equal to 50. So the spring force is exerting a force equal to negative 50x. And I can plug that in for my force here. The direction I'm doing is the x direction, so ds becomes dx. And this is my x initial, which is 0.6 meters. Notice how I want to do everything in meters here. That's very important. My x final is 0. So now I'm simply integrating the function of negative 50x dx. I know you guys have all been eagerly awaiting your chance to do an integral. Here it is. Finally, at long last, you get to do an integral in this class. And what a wonderful thing to integrate, x dx. Woohoo! Okay, that becomes x squared over 2. And those are my limits. Plug in my values, and I get 9 joules. So I'm solving that the spring is doing positive work. Let's just make sure that makes sense. Well, while the spring is pulling the mass to the left, and the object moves to the left. So yes, it makes sense that the spring should be doing positive work, as we found. One more example. Here we have the force exerted by a spring as a function of the distance of the spring is compressed. The equilibrium position is at x equals 0. And I want to know how much work did the spring do in bringing the mass from the position x equals 4 to the position x equals 2. Okay? So if I wanted to, I could write an equation for this line and then integrate it. That's one possible way to solve. Another way is just to take the area underneath here, okay, to calculate the work. And so what I want is the area from 4 to 2. I want this area. So how can I calculate that? Well, if I remember the area of a trapezoid formula, I would use that, but I always forget the formula for the area of a trapezoid. So instead, I'm going to take the area of this triangle and then subtract out the area of this triangle. And then I'll be left with this area here. Okay. So my work is going to be the area, so it'll be 1/2 times my base, so this is the blue triangle, the base is 4, times my height, which is -4. And then I'm going to subtract the area of this triangle, which is 1/2 times the base, which is 2, times the height, which is -2. Okay. So I get -6 joules. Now the reason I'm getting negative work is that this is below the horizontal axis. And unfortunately, you know, the math doesn't let me distinguish between if the mass that's attached to the spring went from a position of x equals 2 to a position of x equals 4. If that's happening, that would be like the mass is stretching the spring out more, because initially the spring is stretched 2 meters and then it's stretched 4 meters. So while the mass is moving to the right, in that case the spring will be pulling to the left, in which case the spring is doing negative work. This problem is different. This problem, the spring is stretched 4 meters and then it's stretched only 2 meters. So the object is moving in the direction that the spring is pulling. So I want the work to be positive. But the math cannot distinguish between did you start here and end here, or did you start here and end here. The math does not distinguish between that. Both of those, if you do the math, will just give you -6 joules. So on my own, I need to say, I'm just going to use the area to find the magnitude. I'm just going to find the number. The number is 6 joules. Then I'm going to figure out whether I think the spring did positive or negative work on my own. And in this case, the spring is pulling the mass from farther away from the equilibrium to closer to the equilibrium. So the spring is pulling it to the left, and the object moves to the left. So I'm going to say the spring has done positive work. Oops, I didn't write it. The spring has done positive work. How much work? 6 joules. Positive 6 joules of work.